Okay, and so next thing we're going to talk about is the quantized energy and the photon. And I took a whole bunch of what was in your book and I just boiled it down to some very simple stuff. I don't really want to spend a whole lot of time on it because it applies to a bunch of different things and we'll work through it in class, all right? And so what we're talking about largely is the photoelectric effect. And the photoelectric effect is a phenomenon that is observed when light shines on some metal surfaces. And when it does that, those metal surfaces releases electrons. And so we can describe the amount of light or the energy of that light as a photon or little bundles of energy. And we can calculate the energy associated with those little bundles or those little transitions using the following equation. And so this was done by Planck way back when. And so the equation is going to just be this: energy is going to equal to Planck's constant, H times V, which we just learned is our frequency. Okay? And so energy in joules, H is Planck's constant, which is that number right there. And again, this transferred poorly. It's not an N, it's nu. It's the frequency indicator there. Okay? So it all is said to follow that equation. And so because of that, we're going to do a sample problem here. Okay? And so the sample problem that I have for you is, what is the energy? Sorry, I wrote in the wrong spot. Okay, so what is the energy of a photon of light, and it's going to be yellow light, with a wavelength equal to 589 nanometers. Okay, now, why did I pick this problem? Because we just figured out the frequency of that, and now that's one less number we have to calculate. So that's what I did. Okay, so from before, we determined that the frequency for that light was 5.09 times 10 to the 14th seconds to the negative 1, or hertz, depending on how you wanted to write it down. So we're going to use this equation right here. So energy is equal to Planck's constant times frequency. And so energy is going to equal Planck's constant, which is 6.626 times 10 to the negative 34 joules times seconds, being multiplied by the frequency, which is 5.09 times 10 to the 14th seconds to the negative 1 power. Okay? Now, again, use your dimensional analysis brain and think about what's going to get knocked out and canceled out in terms of units. So I have seconds in the numerator here, I have seconds in the denominator here, and because those are in opposite sides of a fraction, the seconds unit gets wiped out, leaving behind a unit of joules, which fortunately for us is the unit we're looking for. So that number times that number, and I get something 3.37 times 10 to the minus 19 joules of energy is how much energy it takes for that transfer of electrons. Now, it's not a lot of energy. It's a really, really, really small quantity, but it is something that we can measure. We'll talk about how and why and where this is important in class, but I just wanted you to see the foundations for how the math works and to know that it's there. So that was it. It was a really painless 4 minutes. So talk to you later. Bye.